Alex, I am supposed to hear you. Hello? Hello?
Please, Professor, you may start.
Yes, but I would like, thank you very much. Thank you very much. So I'm very happy to give this talk at this Biennale event. So this year I was not able to come, and but I'm very happy to be allowed to give my talk online. And actually, I have to say that I decided recently to try to stop taking flights, and at least oversized flights, for evident reason, I think. For example, now in France, we had a very strong warm season, and with almost no water in the fields, and it's becoming a real problem. And probably it's not very efficient to do it individually, but at least I think it is important to start trying individually to reduce these all the reasons which are making this climate change now. So let me now begin with mathematics. So what I would like to do is to explain recent results about polar exploration of normal complex surfaces. So I prepared a beamer, and actually I wanted to draw on my iPad, but I was not able to connect it on the system. So I will comment the slides of this beamer. And actually, I had few to draw, so it should work this way. So first of all, let me present my three collaborators on this project. André Bellotto da Silva, who is in Paris now, and Lorenzo Fantini, who is a professor at École Polytechnique, so in Paris too, and András Nemeti at Rényi Institute in Budapest. And my talk concerns mainly results from three recent papers. The two first are written in collaboration with Bellotto and Fantini, and are already published. And the last one, on which is mainly based my talk, is a common work with András Nemeti in addition, and will appear soon in Transactions AMS. So the problem is the following. So I will start with very basic results. Take X0, a complex surface germ with an isolated singularity at the origin, and consider an embedding of X into a Cn for n sufficiently big. And then what you obtain, do you see the arrow on my screen or not? No, probably not. But what you obtain when you intersect X with spheres, S0 epsilon of radius epsilon centered at the origin, you obtain an intersection with X, which is called the link of X. And in the case of a surface germ, what you obtain is a three-dimensional manifold. And the very classical conical structure theorem tells you that when epsilon is sufficiently small, then the intersection of X with the ball with radius epsilon is homeomorphic to the cone over the link of X. In other words, in order to understand a neighborhood of the origin in X up to local homeomorphism, then you simply have to understand the topology of the link X0, okay? And for example, take the link of the singularity E8, so the classical hypersurface in C3 with equation x squared plus y3 plus z5 equals 0, then the link is a Seifert manifold with based a two-sphere and three exceptional Seifert fibers. So it is a very well-known result. And more generally, in order to understand the link, what you can do is that you can consider a good resolution of your surface. So again, you take a complex surface germ with an isolated singularity and consider pi 0 the minimal good resolution of X. So by good, I mean that the exceptional divisor E, defined as the fiber over the origin, is a simple normal crossing divisor. And so what you obtain, so here I wanted to draw something, but for example, if you take the Briançon-Speder family, you see this equation on the screen. T there is a parameter, so you have a family of surface, hypersurface in C3, parameterized by T. So when you take a minimal good resolution of such a surface, the exceptional divisor consists of two curves. One of them is P1, a projective line, and the other one is a curve with genus 8, okay? The curve with genus 8 has intersection, self-intersection -3, and the other one has self-intersection -2. And then from this minimal good resolution, you can associate the dual graph gamma pi 0, whose vertices are in bijection with the irreducible components of the exceptional divisor E, and the edges are in bijection with the intersection between the irreducible components. So there you have only one intersection points between the components. And each vertex is weighted by the genus of the curve, written into brackets, and it is ignored when this genus is 0. And you add a second weight, which is the self-intersection of the curve in x pi 0. So there you see -3 and -2. And so you get this dual graph. And by classical result of Mumford and of Walter Neumann, the data of the topology of the link Lx0 is determined, and it is completely determined by the dual graph gamma pi 0 by using classical plumbing calculus. Okay, so then you have the topological classification of X, which is equivalent to the data of the topology of the link, and which is itself equivalent to the data of the dual graph gamma pi 0. And for example, to give another example, take the singularity E8, and then you get the the classical graph with 8 vertices that you can see on my slide. Okay, and so all these is some topological data. And now I would like to add extra data, which is not a priori, which is absolutely not of topological nature. I would like to add 2 natural families of curves on my complex surface germ. The first one is the family of generic hyperplane sections of X0. So imagine your surface is embedded in Cn, and now in Cn, take an n-1 plane, so a hyperplane in Cn, H, and consider the intersection between H and X. So what you get for H generic, what you get is a curve on X, which is called the hyperplane, unhyperplane section of X. Okay, so you get a germ of curves. So there, I wanted to draw a picture of the surface of H and of the intersection giving a curve. And I wanted to explain that actually such a hyperplane section is resolved by the blow-up of the origin of X. And more than that, actually, for Zariski open set in the Grassmannian Gn-1 Cn, so for H in an open Zariski set of the Grassmannian, you obtain a family which is equisingular in terms of resolution and which has no base point for the blow-up of the origin of X. In other words, what you get is the following. So I will call U this Zariski open set of Grassmannians of hyperplane in Cn, and then I will consider this equisingular family parametrized by H in U. And what I just said is that it is resolved by the minimal good resolution of the surface X, which factors through the blow-up of the origin. And in order to fix the ID, I first give the example of E8, so x squared plus y3 plus z5 equals 0. And there, what you obtain is that the minimal resolution, whose graph is drawn there, factorize through the blow-up of the origin. And the red arrow on my picture corresponds to the strict transform of the generic hyperplane section. But now if you go to the Briançon-Spader family, so my previous example, on that example, you can, with some computation, see that actually the minimal resolution does not factorize through the blow-up of the origin. And actually, in order to get the one which factorize, you have to distinguish the two cases, t equals 0 and t different from 0. Okay? And what you get is the two graphs you see in the middle of my screen. So for t equals 0, the generic hyperplane section has only one component and is obtained by blowing up the intersection, twice the intersection between the two original irreducible curves, while in the case t different from 0, the hyperplane section has 3 components, and you have to blow up 2 points on the genus 8 curves to make the resolution of the irreducible component of the blow up of the point appear, as you see on the second drawing. Okay, so this shows you that the data, the generic hyperplane section family is absolutely not a topological data. Okay, you have to really work in order to make the minimal good resolution factorizing through the blowing up to appear. So this is my first family of natural family of curves on X, and I will always symbolize it by red arrows. And now let me go to my second family, which is the family of generic polar curve. So what do I mean by this? So I start again with a surface germ in Cn, and now I take an n-2 plane in Cn. I call it D, okay? And I consider the generic projection from the linear projection L from Cn to C2, whose kernel is D, okay? And so if you take now D generic, and when you restrict L to X, you obtain a finite morphism. The sentence finite morphism is not on the right line. Okay, it is LD. The restriction of L to X is a finite morphism for D generic. And now consider the polar curve of LD, which is defined as the closure of the critical locus of LD on X minus 0, you get a curve on X, which is called the polar curve of LD. Okay, and if you think about, you can imagine that pi d is the apparent shape of X in the direction D. Okay. And what I wanted to explain there is that with the same kind of arguments as before, this family of polar curves is equisingular if you take D in a Zariski open set of the Grassmannians GS-2Cn. And moreover, the minimal morphism which resolve the base points of this family and which resolves in family these curves is the Nash transform of X. Okay, and to summarize, so consider omega this Zariski open set in Gn-2Cn and consider the equisingular family of polar curves. If you want to resolve the surface and this family, you have to take the minimal, at least the minimal good resolution factorizing through Nash transform. And again, as in the previous case, it is not a topological data. Indeed, take the E8 singularity, x squared plus y3 plus z5 equals 0. If you want to resolve the family of polar curves, you have to blow up twice the bottom vertex of your graph, the -2 leaf of your graph, okay, on the top of your graph, sorry. And then what you obtain is two new curves, and the last one correspond to the exceptional divisor of the Nash transform. Okay, so you get the second graph on which I draw the polar curve, which has a single irreducible component. So I draw strict transform of the polar curve by an arrow on the graph, okay, a blue arrow. So in the sequel, the generic polar curve will be in blue, okay? So I have two now families of curves, generic hyperplane sections and generic polar curves. And what I would like to do is to study their positions on suitable resolution graphs of X. And so to make this question more precise, consider a good resolution of your surface, pi. A priori, it does not factorize through the blow-up of the origin or through the Nash transform. And now consider one generic hyperplane section, H intersection X, and define for any for any curve EV, irreducible component of E, you consider the intersection between the strict transform of H intersection X and EV, okay? And then you obtain an integer that you called small LV, okay? And now you can consider the vector L pi consisting of the collection of LV for V vertex of the resolution graph of pi. And then you get a vector consisting of n integers, where n is the cardinal of the set V gamma pi of vertices of gamma pi, okay? And you can do the same with the polar curve. Take a polar curve of a generic projection of your surface, and you define PV as the intersection of EV, an irreducible component of E, with the strict transform of your polar curve. And then, in the same way, you can define the vector P pi of such integers PV, okay? So now what you get is a triplet, gamma pi, the resolution graph of pi, L pi, so the intersection vector of the generic hyperplane section with the components of E, and P pi, the same for the generic polar curve, okay? And of course, a special case happens when the good resolution pi factors through blow up of the origin and through the Nash transform, in which case L pi counts simply the red arrows on gamma pi for each vertex, and P pi counts the blue arrows on gamma pi. For example, if you take again E8, the triplet gamma pi, L pi, P pi is simply summarized by the resolution graph factorizing through Nash on the blow-up with the blue arrows corresponding to the polar curves and the red arrows corresponding to the hyperplane sections. Okay? And now let me go to the questions. What is polar exploration, which is more or less the title of my talk? So you can address several types of questions regarding this triplet. Actually, all that is motivated at the origin by the famous question of Ledung-Trang about the duality between the two main algorithms of resolution of surface singularities. So there are two such algorithms. The first one is due to Zariski in 1939. It consists in, it tells that you can resolve a surface singularity, a normal surface singularity actually, by a finite sequence of normalized point blow-ups, okay? And so, of course, through such a sequence, the first components appearing are exactly the irreducible components of the blow-up of the origin of C3. Okay, and also you can resolve surface singularity by a finite sequence of normalized Nash transformation. This result is due to Mark Spivakowski in 1990. And there, the first irreducible components of the exceptional divisor appearing are precisely the one corresponding to the Nash transformation of the original surface. Okay, so if I go back a little bit by the first algorithm, I first get the vertex on the extreme right of my graph, while by the normalized Nash transform, I get the top vertex of my graph there. Okay, so a priori, the two algorithms has nothing to do. And a vague question of Lé asked, are these two methods, these two algorithms, dual in a certain sense? And now let me make this question a little more precise. The first natural question, when you see that Nash transform is related with the family of generic polar curves and blow-up of the origin is related with the family of hyperplane section, so the first natural way to do is to consider questions around the triplet gamma pi, L pi, and p pi. So the first question is, does the topological type of X0 restrict the possibilities of the triplets gamma pi, L pi, p pi? In other words, starting from the topology of X or from the minimal resolution graph of X, can we recover all the possibilities for these triplets? Are there a finite number? And are there a finite number assuming that gamma pi factors through Nash on the blow-up of the origin, and so on? Okay, this is the first question. Another question, also very natural, is can we find special classes of surfaces for which this triplet is determined by the topological type? Okay, we previously saw that it is not a topological data, but are there special type of surfaces for which it is the case? Another question, maybe closer to Lé questions, is how the two vectors L pi and p pi are related. Is there a natural relation between them? And eventually, the last question, which is really what we call polar exploration, you give yourself the two graphs gamma pi and L pi, and preferably with gamma pi factorizing through the blow-up of the origin. And the question is, find the possible vectors p pi. Okay, and so it is really what we call polar exploration. So it has nothing to do with this picture actually. And so I will try to answer. We have answers for all these questions, and I will try to present part of what we did. So first, what we did with András in the third paper I mentioned before is to give positive answer to question 1. So what we proved is the following result. So you start with a topological data, as I said. So in other words, you start with M, a real 3 manifold. And and you try to recover the underlying triplets gamma, L, and P. So the result is that there exists finitely many triplets gamma, L, P, where gamma is a weighted graph and L and P are vectors whose parameters are in bijection with the vertices of the graph gamma, such that there exists a normal surface singularity X, such that first, the link of X is homeomorphic to the 3-manifold M, and secondly, the triple gamma LP equals gamma pi L pi P pi, where pi is the minimal good resolution of X, which factors through the point blow-up and the Nash transform. Okay, so starting, in other words, starting with any minimal resolution graph with, as you know, negative definite intersection matrix. So starting with that, Grauwert tells you that all the normal surface singularity have such a minimal plumbing graph, and that any such plumbing graph can be realized by as the link of a surface singularity. Okay, so now starting with such a data, you can recover all the triplets gamma pi, L pi, P pi. So the proof is a little bit technical, fairly technical actually. And so there I give the steps. So you start with gamma, the dual graph of the plumbing graph of M. So it will be the minimal resolution graph of X, okay? The first step consists in bounding the multiplicity of X. Once you have this, you are able to bound the vector L pi. Then, once you have this, you are able to bound the number of blow-ups for pi to factor through the point blow-up, okay? As I did previously for the Briançon-Speder family. After that, second step, we are able to bound the vector P pi, and then last step, we are able to bound the number of blow-ups for pi to factor through the Nash transform. So these are very natural steps, okay? And I will give more details now on the proof. I will start by, I will show you how to first bound the multiplicity of X, just having the topology of the link. For this, I need the Lippmann cone of a surface. So start with X, a normal surface germ, and consider a good resolution of X and its dual graph gamma, so gamma pi, but for short I write it gamma. And consider now the set of vertices of gamma, V1 and so on, Vn, and the intersection matrix associated with gamma, which is simply the matrix of intersections between the curves, irreducible components of the exceptional divisor E. Okay, so this data is completely given by the dual graph gamma. Okay, from this, you can consider the semigroup generated by the components E1, EV1, and so on, EVN of E. Okay, in other words, it is the semigroup of divisors D equals sum of dv EV, okay, where dv is an integer. Okay, so now what we want to do is to consider the Lippmann cone E plus, and it is the subsemigroup of G, which consists of the elements of G, which whose I didn't write that, but whose coefficient dV are positive, okay? And secondly, what we want is that the intersection between D and each EW, for W a vertex of gamma, is less or equal to 0, okay? And so what you obtain is, if you want to now draw the vectors corresponding to components of the Lippmann cones, okay, vectors dv1 and so on, dvn. I wanted to draw it there, but now I will go to my last slide because I wrote it on my last slide. So what you see is exactly the blue cone, the sector which is limited by the blue cone you see on the right of the picture, okay? And in order to see that, what you have. So I will return back to the definition I had. You see that E plus is just the inverse image by minus I gamma, so the intersection matrix transformation minus I gamma. So it is minus I gamma minus 1 of the positive quadrant, okay? Because I want that D point EW is less or equal to 0. And so what you get is this cone, okay? This what I draw as the blue cone. And why we introduce that? It's because now take an analytic function, germ, on x, f, from x0 to c0, and consider is associated divisor, f gamma, the sum of MVF EV, where MVF is the multiplicity of f along EV, by a classical theorem of Laufer from 1971. For all W vertex of gamma, the intersection between the divisor f gamma and EW equals minus f star EW, where f star is the strict transform of f. So what you get is indeed a negative number. And it tells you then that this divisor f gamma belongs to the Lippmann cone. Okay? And so now we would like to see, to argue on the Lippmann cone. The problem is that not all points of the Lippmann cone are, if you fix the surface x0, not all the points of the Lippmann cone are associated with the divisor of such a function, an analytic function. And so it is a problem if we want to bound the multiplicity. So for example, if we want to see who is the generic linear form on X. But there is a very nice theorem by Kobel, Nemeti, and Popescu-Pampou, which tells you the following. So you start with a weighted graph, and you consider a non-zero divisor on gamma, D equals sum of AV, EV, which is sufficiently big. So with sufficiently big parameters, coefficients AV, In other words, such that D intersection EV plus a certain amount which only depends on gamma. This amount is the valuation, the valency of V, which is by definition the number of incident edges of V, plus 2 times the genus of V. So this is a positive quantity. So what we want is that D intersection EV plus this positive quantity, which is a topological data, is less or equal to 0 for every vertex V. Okay? Then what Kobel, Nemeti, and Patrick Popescu-Pampou proved is that then for every normal surface singularity whose link has gamma as a plumbing graph, you can find a function with an isolated singularity which realize D as the divisor. Okay, you can find F such that D equals F gamma. And moreover, if you work a little bit more, you can obtain that the total transform of F, so F gamma plus the strict transform, is a normal crossing divisor. Okay? And now, what I wanted to write, but I don't have my iPad, so I will just say it. You see, there is a space between 2GV in my formula and less or equal to 0. Now you can improve that theorem by adding +2. Okay, so by taking a divisor which is even bigger, and if you add +2 to the definition of D, what you are able to find is 2 functions, not only one, but 2 functions F and G, which realize this divisor, okay, such that F gamma and G gamma will be equal to D, and such that the 2 strict transforms of F and G does not intersect. Okay, so you can move the strict transform of F to obtain another function. You can move the strict transform of F and G in the resolution to obtain disjoint strict transform. Okay, and with this improved theorem, you can prove the following proposition. Give yourself a weighted graph, then for every normal surface singularity, x0, which admits a good resolution pi whose weighted dual graph is gamma, then the multiplicity of x is less than a topological number n gamma defined as minus d square, where d is the divisor defined in the theorem before, okay, and which is of a topological data because it only depends on the valency of the vertices, the genus of the vertices, and the incident, the intersection matrix. Okay? How to prove this? It's very simple. Take 2 functions f and g as in the improved theorem and consider the morphism phi equals fg from x to c2. Then it is very easy to see that the multiplicity of x is less or equal to the degree of phi. But the degree of phi is also very easy to compute because you just have to intersect the total transforms of f and g. But now, since the strict transforms f star and g star does not intersect, what you obtain is nothing but minus d square for the degree of phi. And then this proves the proposition. So now we have bounded the multiplicity by a topological bound. Okay, so now what I want to do is to explain how to bound the vector L. And for this, you consider the divisor Zmax, which is the sum of MV EV, where MV is the multiplicity of a generic linear form along EV. Okay? In order to bound the vector LP equals LV, defined before, with the generic hyperplane section, what you do is the following. Of course, we have that MV is less or equal to EV because AV is the multiplicity of a function f, okay, on the graph. And then for each V, the multiplicity of a generic linear form must be less to the multiplicity of any other function, okay, on X. So MV is less than AV, so it enables one to bound MV, okay? And so it enables one to bound the amount of possible divisors, Zmax. And now we use again Laufer's results, which tells you that for each V, you have Zmax point EV plus LV equals 0 for all V, okay? And then this determines a finite number of vectors MV by the first line, and then this gives a finite amount of vectors L pi, okay? Now, we have to bound the amount of blow-up to obtain the minimal resolution which factorize through the point blow-up, okay? And for this, we will use the result of Wagreich, which tells you that the sum of MVLV is less or equal to the multiplicity, okay? And remember that we have bounded the multiplicity by a topological data. So now all we have to do is to control this sum of MVLV under point blow-up. And indeed, if you consider pi prime, the point blow-up of a base point of the family of generic hyperplane section, what you obtain is that this sum of MV, LV will strictly increase, okay? And since it is bounded by n gamma, it means that after a finite amount of point blow-up that you control by n gamma, you will resolve the base point of this family. Okay, so this proves that you indeed have a finite amount for gamma pi, L pi, providing gamma for gamma pi factorizing through the point blow-up. Okay, now if you want to bound the vector, the polar vector, what you can use is the Legge-Royol-Tessier formula, which tells you that the polar multiplicity, the multiplicity of a polar curve, defined as the sum of MVPV, you can compute it that way, is also equal to the multiplicity of X minus the Euler characteristic of the Milnor-Ley fibration of the generic linear form. And this is completely determined by the pair gamma L determined before. Okay, so if you fix gamma L, there are only a finite number of possibilities for P because you bound not only M pi 0, and after that you can bound, you can use the equality m pi 0 equals sum of mvpv, okay? And now the remaining part of the proof consists in bounding the number of blow-ups to factorize by the Nash transform. And I won't I won't finish that proof because it is fairly technical. It uses Keller differential on X, and in particular, the zeroth fitting ideal sheaf in the resolution. But our arguments are again based on the previous improvement of the Kobel-Nemeti-Popescu-Pampus theorem. In other words, we use two forms defined as df wedge dg, where n, f, and g are given by the theorem. But I won't enter in this technical detail. Please, can you tell me how much time I have now? Hello? Hello, hello? You hear me? I see you, Alex. Can you tell me how much time I have now?
Enough?
3 minutes. Okay, I have 3 minutes. Perfect, thank you. Thank you. So now I will just answer rapidly question 2. When does the topology determine the triplet gamma pi, L pi, P pi? Okay. For this, I need to recall rapidly what Lipschitz normally embedding is, and I think that you already had several talks mentioning that. At least the talk given by Elie on Tuesday, for those who attended. But let me remind this in 1 minute. So you start with a complex analytic germ in Cn0, and you define on X 2 metrics. The first one is the outer distance on X, which is simply the restriction to X of the standard Hermitian distance of Cn. And the other one is the inner distance, which is defined as the infimum of length of arcs from the 2 points for which you want to compute the distance. So you take 2 points, X and Y on X, and you consider all the rectifiable arcs between X and Y, and you take the infimum of their lengths, and you obtain what is called the inner distance between X and Y. And a germ is said Lipschitz normally embedded if inner and outer metrics on X are by Lipschitz equivalent, which is equivalent to say that you can locally bound the inner distance between 2 points by k time the outer distance between the points. Locally means in a neighborhood of the origin. Okay, so now when does topology determine the triplet gamma pi, L pi, P pi? There is, and I will end with this slide, there is a very nice, two very nice results by Spivakovsky in his great paper devoted to the resolution by normalized Nash transform, and another one by Romain Bondil in 2003. And so summarizing these two results, you have the following. If X is a minimal surface singularity, which is a very special type of surface singularity among rational singularities, then the topological type of X determines the triple gamma pi, L pi, P pi, pi being the resolution factorizing through Nash and the blow-up of the point, and secondly, the topological type of the discriminant curve of a generic projection. Okay, and so for minimal surface singularities, this is a topological data. And recently, with Fantini and Bellotto, we proved that the same is true when you consider a normal surface singularity, which is Lipschitz normally embedded. And actually, theorem 2 is a generalization of theorem 1 because a few years before, we proved with Walter Neumann and Helge Pedersen that actually minimal surface singularities are themselves Lipschitz normally embedded. Okay, so I will stop now. Thank you very much for your attention, and I would like to congratulate Osamu Saiki. Thank you very much.
So, are there questions in the YouTube chat first? No? Okay. Are there questions? Comments?
So you found this bound on how many different triples there can be. Do you have a way to determine if you have a given triple, if it's actually realizable?
It's a very good question. First, hello, Elia. I recognize your voice, and now I see you. It's a very good question. First of all, the theorem I stated on the basically proved, okay, give you a very large bound on the amount of triple, okay, and so all these triple are all the triple given by our proof are far from being realizable. And actually, we have ways based on other results, for example, the Laplacian formula that maybe you know, which relate p pi, l pi, and the inner rates of the normal surface. And with this tool, we are able to drastically reduce the amount of triple, okay? And so your question will be really for this now very small amount of triple we determine with the Laplacian formula. But actually, the answer for the moment is no. We are not sure of being able to realize all the triplets we can find. Okay, but even if you take complicated, examples, actually, most of the time you get only one or two triple. It's something very surprising. The proof gives you, I don't know, 100 of possibilities a priori, but if you use other tools, combinatorics like the Laplacian formula or topological arguments about generic projections, you will reduce very drastically the amount of triples. But I don't know whether all of them are realizable.
Okay. More questions? Mark, Terry?
Thank you for a very nice talk, Jan.
Okay. So Max
from
Terry. Okay.
Can you say how many exceptional lines there are?
Can say it again? I didn't get the question.
You have the data of the triple.
Yes.
Can you say how many exceptional lines there are from the data?
How many what?
Exceptional lines in the tangent cone.
If I have the triple gamma LP, where gamma factorize, and if I know that gamma factorize through the blow up of the points, then yes, I have exactly the amount of irreducible curves in the tangent cone. Right. Hello? I don't hear you. Yes, I see you. Okay.
Suppose we have a family of surfaces and the triple remains constant in the family. What can you say about the relation between the members of the family? And one of the things I had in mind with the relation was the thick-thin decomposition of the members of the family.
But the triplet, alors, when you say the triplet, you assume that it factorizes,
Yes,
it
that's
corresponds to a triplet factorizing through the blow up on the Nash transform. Okay,
Yes.
but if you limit even to the blow up of the point, the pair gamma L gives you the 16 decomposition, because then L gives you the strict transform of the generic hyperplane section,
Yes.
okay, and the irreducible components of the tangent cone correspond exactly to the vertices of the graph which carries arrows. Okay?
Yeah.
And then the underlying irreducible components are exactly the one corresponding to the projectivized tangent cone, and then they correspond to the seek part. And
Right.
and now you add, if you want only the 16 decomposition, you add the adjacent bamboos to these vertices, and you obtain the seek part. You obtain the conical part if you see only the vertices, and in order to get the seek part, you have to add the adjacent bamboos. It answers your question?
Well, to start.
Okay.
To start. Thank you.
Mark.
Thanks for a great talk.
Thank you. So you are Mark Spivakowski, right?
Right.
Right.
I just have a quick question. That in one of the papers you cited there is a word valuation in the title, but you didn't talk about where do valuations come in.
Yes, but I didn't speak about. I didn't speak about this part. It is about. It is about what we call the Laplacian formula. Okay, the Laplacian formula gives maybe I can show rapidly, but no, I will just explain you. So now, if you want to consider all the good resolution of the surface at the same time, okay, then you will have to deal with functions defined from the non-Archimedean link of the surface, okay? And in this non-Archimedean link, who was intensively studied by Lorenzo Fantini in his thesis, you can embed all the good resolution graph of the singularity. And it's very convenient. Instead of studying vectors associated with a resolution graph, such as P, L, and so on, it is more convenient to study functions defined on the non-Archimedean link of the singularity, okay? And then you have a wonderful phenomenon appearing, okay? And in particular, you can also, with that, have a non-Archimedean flavor of the matrix defined on X. And it is why we did that. But actually, you could ignore this part if you want just to use this Laplacian formula on one precise resolution graph. Okay, and it is what I did more or less in my talk today.
Okay. Okay, thank you.
Okay, and thank you very much for your talk. And it's very
Thank-
nice. Thank you.
Thank you.
Good morning. It's a pleasure to introduce the speaker, Marcos Kreiser from PUC Rio de Janeiro, Brazil. His areas of interest are affine differential geometry and singularity theory. His research involves also topics in discrete geometry, considering application in computer vision. He's talking about singularities of generic lines congruences.
Thank you for the presentation, for the invitation to this meeting. It is really a pleasure to be here in São Carlos in this meeting that I like so much. It is really important for me to be here. And so thank you, Cidinha, thank you, Raimundo, all the organizers. And I would like also to congratulate Saeki for his 60th birthday. So very nice age. I hope you can still have many fruitful years in the future. Okay. And I'll talk about this theme is line congruences. It has this old name, but it is just a two-dimensional family of lines in R3. So I will start explaining this. So this is the outline of talk. I will explain what is a line congruence, the main ingredients. Then it has its principal directions and discriminant curves, which are the main elements of a line congruence. Also principal lines, and ridges are also another important ingredient of this line congruences. And finally, I will introduce the equiaffine pairs, which are the main technique that we have used to prove our theorems. I must mention that this is a work, joint work with Ronaldo Garcia. So, a line congruence is a smooth two-dimensional family of lines in 3 space. Some well-known examples are normal lines to a surface in Euclidean space, normal lines to a surface in Minkowski space, affine Blaschke normal lines to a non-degenerate surface in the affine 3 space, lines connecting points of true surface with parallel tangents, lines connecting points of 2 curves in 3 space, tangent lines to one family of asymptotic curves of a hyperbolic surface. And there are many other examples of natural family of lines that occur in geometry. And a line congruence is determined by smooth functions f and xi. F is a point, xi a direction of the line. Then we can consider the line congruence map, which is just the line with the point fu plus with the direction xi. This is a map from R3 to R3, a 3-dimensional manifold to a 3-dimensional manifold. And the generic singularities of this map are folds, cuspidal edges, and swallowtails. This was proved by Izumiya, Sashi, Takeuchi in 2003. And in this work, we try to give geometrical descriptions of these singularities. The shape operator is important here. It's just when you differentiate the normal, the vector fields C, decompose it into the base F, which are the derivative Fu, Fv, and Xi. the tangent component is called the shape operator. The singular set of the line congruence corresponds to P equal to inverse of the eigenvalue, where lambda is the eigenvalue of the shape operator. The focal surface is the envelope of the two-dimensional family of lines. It is generally a singular surface. It has two leaves given by these formulas. Then the focal set is the image by the congruence line map of the singular set of its singular set. We have to use Plucker coordinates in the space of lines, which are well known. They are explained here. Consider homogeneous coordinates of 2 points of the line. You calculate these determinants and then obtain the Plucker coordinates, which are in projective space P5, but they must satisfy this relation, which determines a quadric in P5, which is a four-dimensional submanifold. So a line congruence more formally is a smooth map from a domain in R2 to the Klein quadric K. We denote by U the space of line congruence. U, I am the space of immersive line congruence. And standard argument shows that U, I am is open and dense in U. And then we define U0, the set of smooth line congruence such that there exists a smooth regular surface defined in a neighborhood of 0 transversal to the lines of the congruence. And the space U0 is open and dense in UM. This is a proposition. So we can always, in this set U0, consider that the line congruence, that the surface is a planar surface UV0, and the vector field has third component equal to 1. So the only, to characterize the line congruence, you just consider a map from C bar from U to R2. And then we can identify the space of line congruence with the space of smooth maps, endowed with this infinite topology. So now the elements, the geometric elements of the line congruence. The line congruence, you can look for, consider subfamilies that which determine ruled surface, which are one-dimensional line congruent. One-dimensional family of lines are ruled surfaces, and they are developable if and only if this condition CFT CT equals 0. This is the determinant, and we write this condition in coordinates with this equation, binary differential equation. The solution are called principal lines. The tangents to the principal lines are principal directions, and it is a fact that the principal lines does not depend on the choice of the surface, neither the vector field. So, and they are also invariant under projective transformations. In terms of the binary differential equations, we can write the binary differential equation in terms of the shape operators, which implies that the principal lines are tangent of the eigenvectors of the shape operator. As a remark, in the literature, you can also find other lines, which are also called principal lines. They are related to Kummer forms. And these are Euclidean invariant of the line congruence. They are also independent of the choice of the surface and the vector field, but they are not projectively invariant. They are just invariant under Euclidean motions. They may be interesting, but it's not, I will not talk about them in this here, okay? The discriminant curve is important, very important in this talk, and you consider the eigenvalues of the shape operator. The discriminant shows when the eigenvalues divide the set when the eigenvalues are complex or real. So when you put delta equal to 0, you divide the parameter set into two regions, one with two principal directions and one with no principal directions. Generically, the discriminant curve is a smooth, regular curve in the parameter space. And if you denote by U1 the set of line congruence such that 0 is a regular value of delta, we can show that U1 is open and dense and U0. And we remark that line congruence that in U1, which are the ones that we shall consider, they do not admit umbilical points. So generically, line congruence can avoid umbilical points. What are linear congruences? Linear congruences is the intersection of a three-dimensional linear space in P5 with the Klein quadric. Some basic examples are line passing through a given point, all lines in a plane, lines connecting two skew lines, one parameter family of line pencils whose vertices are in a line and whose planes contain the same line, real lines intersecting a skew pair of complex conjugate lines. Please.
You need two linear relations to define a linear congruence,
Yes.
and you said one.
Three-dimensional linear space in P5. You have to have two conditions. Yes. So, there are three types of linear congruence. They are called hyperbolic, parabolic, and elliptic. When they contain lines in Klein quadric, because the Klein quadric contains some lines, and then these are the conditions to describe it. We can consider the tangent plane of a congruence. At a given point, its tangent plane may contain 2, 1, or 0 lines in the Klein quadric. In the first case, any linear congruence containing this tangent plane is hyperbolic. In the second case, any such linear congruence is parabolic, and it's elliptic in the third case. All the calculations were done locally, so more important than the vector field are the shape operators. So we consider these jets of the components of the shape operator, A, B, and C, and D. This condition is just for the existence of the C1 and C2, the vector field. And also these conditions are just for the existence of this vector field C. In the model, the Plucker coordinates are given just a calculation. The derivatives of this immersion is here. Omega 1, omega v. This is nothing. Thus the plane, we have to consider also the initial point. And then conclude that the tangent plane contains two lines of k if you are in the delta greater than 0, or which means two real eigenvalues. When we have just one real eigenvalue, just then you have just one line of the Klein quadric, so that any linear congruence is parabolic, and here you are in the set of the elliptic congruences. I will talk now about what happens at the discriminant points. That's what are more important to us. Ridges. Let me see. Ridges is after. Okay. A discriminant curve, the shape operator, we may take coordinates so that the shape operator is like that. In the diagonal, A0 is equal to D0, B0 is equal to 0. And since they are not umbilical, C0 different from 0. And a discriminant point is regular if the principal direction is not tangent to the discriminant curve. Otherwise, it is called singular. The origin is singular if the B01 equal to 0. This is all immediate. And since the 0 is a regular of delta, we have that B10 should be different from 0, just to make the calculations. What time I have? It's 15 minutes. Okay. Here we calculate the generic behavior of principal directions. This is quite standard. You consider the surfaces f equal to 0, corresponding to the solutions of the binary differential equations. This f equal to 0, you can just put as a function of v and p, and the direction filed is then written with this equation. At the origin, we have this fp is equal to 0, because the 0 is equal to a0, and p is equal to 0 also in our model, and fv is this guy here, which is 0 if and only if the tangent, the principal direction is tangent to the discriminant curve. So we conclude that the singularities of the above equation coincide with the singular points of the discriminant, and at a regular discriminant point, the principal line is a cusp. To see what happens in a singular part, we have to consider the linear part of the differential equation, which I call it W. Associated to this matrix, we have two important discriminants. This is delta 1 and delta 2. Delta 1 is just the determinant. Delta 2 is this other one. I'll explain here. Denote the direction of an eigenvector of W. The projection of the direction are called the separatrices of the singular discriminant point. At the origin, the beta defines a separatrix if and only if it satisfies this equation. The discriminant of this equation is delta 2. If delta 2 is bigger than 0, there are two separatrices. Delta 2 smaller than 0, no separatrices. delta 2 equals 0 means geometrically that the contact of both separatrices is of order equal or bigger than 2. The condition delta 1 equal to 0 means that the contact of the discriminant curve with the separatrix is of order bigger or equal to 2. Here are the important figure. In red is the discriminant curve, so there are only principal direct lines in one side of the curve. This black, thick black, are separatrices. In this case, there are 2 separatrices, which are also principal lines. And here in blue and green are the ridge curves that I will explain later. But from this picture, we can describe all the behavior of the line congress. So returning to describing the principal lines, if delta 1 smaller than 0, the origin is a folded saddle. Delta 1 bigger than 0, then we have 2 conditions. Delta 2 bigger than 0, folded node. Delta 2 smaller than 0, folded focus. An example is we can consider this shape operator when epsilon equal to 0. These shape operators correspond to a Darboxian umbilical point. Thus this example can be seen as an unfolding of a Darboxian umbilical point. The curve delta equals to 0 is an ellipsis, and the principal lines are sketched in the next slide. These are the 3 possible topological behavior of the unfoldings of umbilical points. This was, in fact, the starting point. We were looking for to understand better the line curvatures at umbilical points, and we are trying to use this blow up to understand it, but it doesn't. We didn't go very far with this idea, but even so, it was an important example for us. Ridges is the third important geometrical curve in this context. What are ridges? They are defined by this equation. The ridge sets are generically smooth regular curves in the parameter space. By this easy calculation, outside the discriminant curve, the ridge points correspond to singularities of the focal surface. The singularity is of type A3 if the ridge curve is not tangent to the principal direction, and of type A4 if the ridge curve has an ordinary tangency with the principal direction. This result is a corollary of a much more general result, which is by these guys here. The ridge equation, and now we are interested in looking what happens with the ridge curve at the discriminant set. A discriminant set point satisfies this equation if and only if it is singular. At a singular discriminant point, we have all these numbers, A0, B1, Q, and then the ridge curve is given by this equation here. The part V smaller than 0 correspond to one ridge, V greater than 0, bigger than 0 correspond to the other ridge. So this is the same figure, we have two ridges, and they are tangent to the discriminant curve at the singular point. This is the general behavior of a ridge curve. And then an important calculation is that the discriminant, assuming that the discriminant curve has a contact with the separatrices of order less than 2, which is equivalent to delta 1 not equal to 0, then the ridge curve has a contact of order bigger or equal to 3 with a separatrix if and only if this happens, this equation. The focal set are, again, we consider this is each leaf of the focal set. At the discriminant curve, the two leaves come together, and we can calculate the derivatives, and we can conclude that at non-singular discriminant points, this focal surface has a tangent plane generated by the image of f star of the principal direction and c. At the discriminant point, the focal surface has only one tangent, namely c. If this occurs, the image of the discriminant curve by f is regular with tangent in the c direction. So the figure is here. This is the focal set, the discriminant curve in red. The focal set is smooth at the discriminant set, even if there are two different leaves, and at a singular point we have a cuspidal edge, and this green curve is the image of the ridge, which is the cuspidal edge, in fact. So the results, the main results of our work is the following. Along the discriminant curve, the only generic singularities are folds and cuspidal edges. At regular points, the line congruence map has folds, which correspond to regular values of the focal surface. At singular points, the line congruence map has generic cuspidal edges which correspond to cuspidal edges of the focal surface. The conditions for cuspidal edge is that the tangency between ridge curve and the separatrix is ordinary. So geometrically, I will return. I am saying that these are the only possible singularities of the line congruence. Here is a fold which corresponds to a smooth point of the focal surface, and here is a cuspidal edge. And the condition is exactly this here, that here we have a cuspidal edge, but the condition is that the blue and green lines is like that. They do not have tangency of order 2 with the separatrix, which are in black. So, for the last part of the talk, I will explain how we have proved this this theorem. Our technique is related to equaffine pairs. What is an equaffine pair? Is a surface together with a transversal vector field, and you write the usual decomposition of a pair Fc. Here we have the metric AXY, and here you have the one form, and the pair is equaffine if the one form is zeros, the derivative of Xi is tangent, and this metric is non-degenerate. And the idea is to represent a line congruence by such a pair. Examples of equaffine pairs: Euclidean normals, affine Blaschke normals, and this is another application of equine pairs, but has nothing to do with the line congress. When you have an equine pair, you have the conormal map, which is important guy here. The shape operator A, B, C, D can be represented by the conormal map in this way here. Where, since this is non-degenerate, we can calculate from the conormal map, you can calculate the shape operator. And also the support function, it's well known. It's just conormal applied to, you have any point in space, you apply the conormal to the difference and from this point to a point of the surface. And this surface has this property here. The second, the critical points correspond to points in the line, where x, y, z is in the line, and the critical point is non-degenerate. This matrix has determinant 0 if and only if P is equal to the inverse of the an eigenvalue of the shape operator. So the focal set is the bifurcation set. Opa. The focal set is the bifurcation set of the support functions, and the singularities of the line congress are the degenerate singular points of the support function. AI points of rho, I equal to 2, 3, or 4, corresponds to fold, cusp, and swallowtails of the line congress. So it's important to have this equine pair because it leads to the support function, and with it we can calculate everything. And the one of main theorem is that outside umbilical points, any line congruence can be represented by equine pair. Since we are in our generic set, we don't have umbilical points, we can apply this theorem in our context. I think it is important to understand what happens at the umbilical points. It may be not easy, probably. But how have we proved this theorem? You consider the line congruence, the shape operator here, and then we looked for solutions of this equation. And outside umbilical points, at umbilical points, this is a identity, and we cannot do anything. But outside umbilical points, existence of solutions of the above partial differential equations are guaranteed by the Cauchy-Kovalevsky theorem. With such a P, you can construct Q by these equations and define the conormal vector field by these guys here. Choose a multiple of Xi, which is Xi tilde, and a different surface, not UV, but this other surface. And these guys, 1 minute. Okay. So these are when you calculate the equine parameters of the new surface, you obtain some calculations here. I will pass through it since singularities. I will pass to the last one. At a singular point, the condition for a singularity to be of type A3 is this here, and at the origin, these are given by these conditions, which can be written exactly like that, with this equivalent to the condition for the order of contact of the regions is separatrix be less than 2. So, thank you, everybody.
Are there any questions, comments?
It's on. For congruences in three-dimensional space, you have for free very nice property for the images of the principal lines, right? Images of the principal lines on the focal surfaces, they form a conjugated net, right? And then I have not understood, maybe you can help me, what happens with this conjugated net on the image on the discriminant line on the focal surface? Are they tangent or are they transverse to the image of the discriminant curve?
Oh, they are tangent. The principal lines are tangent to the discriminant curve at the singular points. But
No. I'm talking about the focal surfaces, of the images of these principal lines and discriminant curve on the focal surfaces.
On the focal surface, they are tangent to the focal surface. It's a direction tangent to the focal surface, and at ridge points it's tangent to the cuspidal edge curve.
All right, thank you.
This is.
As you mentioned, an example of congruence of lines is the normal to a surface, and then also to all the parallel surfaces. But in the case that you are this family of lines, therefore, in general, locally, they define some plane field. Family of lines of R3. If you look at the planes orthogonal to a line at a point, you have a plane. So locally, you have a plane field in R3, which in general is not integrable. And when it's integrable, it's the case of the normal to a surface. So how you see the non-integrability of this normal plane field in your formula? That's the first question. And second question is, at a point of R3, if you take the normal plane to the line, you can locally, as parameters of your family of lines, take just an open set on this plane in the neighborhood of the point where the plane is orthogonal to the line. And my question is, what do you see in your particular singular points? If you look at this special family of parameters for your congruence.
Let me see, Remy, if I understand you. You're saying that for special parameters, it is, they call it a normal line congruence, which there exists a surface such that the lines are normal to the surface. This is, you are asking if if in this context, the focal set is different.
Not exactly. In the case you don't have integral surfaces to the planes, then measure or see this non-integrability of the plane field, the fact that there is no foliation tangent to it, in your formulas. That was the first question. And the second is also in this non-integrable case, just locally, if you take as parameter a neighborhood of the point where the line is intersecting the normal plane, so this is locally parameters, what could you see better or something special if instead of general parameters for your family, your congruence, you just take this type of parameters on a plane which is orthogonal to a line at the neighborhood of the intersection point?
Yes, the first one I cannot see because your family of planes is orthogonal to C, and our calculations are not looking at orthogonality, so I cannot see them, these planes. But for you to find conditions for the line to be a normal congruence, you have to describe the Euclidean structure of it. The second question is if you consider just normal congruence, of course, then this theorem does not hold anymore, of course, because at least you have umbilical points and many other things generically. So you have to, in fact, we have to consider other structures because.
Okay, thank you.
Let's thank the speaker again.
Obrigado.
Ele pode deixar ligar. Não atrapalha aqui. Eu coloco. Sim? Cadê o coisinha? Cadê o coisinha? Ah, tá. Deixa eu testar aqui.
Hello, everyone. It's a pleasure to introduce the next speaker, Bárbara Caroline de Lima Pereira. She defended her PhD thesis in his year under supervision of Professor João Tomazella at UFSCar São Carlos, where she studied Bruce Roberts numbers of a function on a ICES. In this moment, she is doing a postdoc at UFSCar. She talked about the relative Bruce Roberts number of a function isolate complete intersection singularity.
Thanks for the presentation. So it is a pleasure to participate of this workshop in honor to Professor Osamu Saeki. So congratulations, Professor. And today I will talk about the relative Bruce Roberts number of a function on an isolated complete intersection singularity. And it is a joint work with Nuno Ballesteros, Orefsio Okamoto, and Tomazella. Okay. Well, in this presentation, I will talk about three numbers: the Milnor number of an analytic function germ and the Bruce Roberts numbers. Okay. So the Milnor number of an analytic function germ F is equal to this dimension, the dimension as a C-vector space of this quotient. Okay. And to calculate the Bruce Roberts numbers, we consider a reduced analytic variety X, and we use this set, the set of the vector fields that are tangent to X. Okay, so the set is the set of the elements in theta n that satisfies this condition for any function germ in this ideal Ix. Okay. And this ideal Ix is the ideal of the analytic function germs that vanish on X. Okay? So the Bruce Roberts number of F with respect to the variety X is equal to this dimension as a C-vector space, and the relative Bruce Roberts number is equal to this dimension as a C-vector space. The difference between the Bruce Roberts number and the relative Bruce Roberts number is this ideal Ix here. Okay. Well, to calculate these numbers, the Bruce Roberts numbers, are so difficult because this set, theta x, okay, it is hard to work with it. And in this presentation, I will to present a relation for these numbers when X is an isolated complete intersection singularity. Okay, and these relations are important because with it we can to obtain information about the logarithmic characteristic variety. Okay. Well, so first I will talk about the relative Bruce Roberts number, and okay, the Bruce Roberts numbers can be calculated considering any variety, but in this presentation I consider only isolated complete intersection singularity. Okay. So the first, the relative Bruce Roberts number. Okay. Wall proves this result. Okay, so when X is a weighted homogeneous ICES determined by this map germ, he proves that theta X in this case is generated by these vectors fields. Okay, so it's generated by the Euler vector field, these vectors fields with j from 1 to n and I from 1 to k, and the minors of maximum order of this matrix. Okay, and with this characterization for theta X, we have this equality for any function germ F. Okay, so this ideal is equal to this sum, and here this ideal JF phi1 to phi k is the ideal generated by the minors of maximum order of the Jacobian matrix of F phi1 to phi k. Okay, well, with this equality, Bruce and Roberts proves this characterization for the relative Bruce Roberts number when X is a weighted homogeneous ICES, okay, and F is a function germ, such that this restriction has isolated singularity, okay. Well, we prove if X is an isolated hypersurface singularity and F is a function germ such that this number is finite, we prove this relation for the relative Bruce-Roberts number, okay? But this proposition is, we consider X an isolated hypersurface singularity. And now we want to know about the ICEs, okay? What is the relation when X is an isolated complete intersection singularity? And we have this example. So we consider the ICEs determined by this map germ, phi, okay? We calculated the Milnor and Turina numbers, okay, of the ICEs. So this ICEs is not weighted homogeneous. And we also consider this function germ. So we calculated the Milnor number of the fiber. And in this example, we have this relation for the relative Bruce-Roberts number, okay? So now I will prove that this equality is true for any ICEs X, okay? Well, so our objective is consider X and ICEs determined by this map germ, and F a function germ such that this number is finite, okay? And we want to prove this equality. Okay, but in this case, we consider any ICEs, we don't know the generators of theta X, okay? And we consider the set of trivial vector fields, theta xt, okay? And theta xt is generated by these vectors fields, okay, with j from 1 to n and I from 1 to k, and the vector fields that vanish the differential of a phi, okay? And this map phi is this map, okay? The map that defines a variety, okay? Well, when X is an isolated hypersurface singularity, we have this characterization for the set, theta xt, because in this case, we know that the partial derivatives of a phi is a regular sequence, okay? Well, we extend this characterization considering X and ICEs determined by this map germ, okay? So now theta xt is generated by these vector fields and the minors of the maximum order of this matrix, okay? Okay, and with this characterization, we have that this ideal df theta xt is equal to this sum for any function f, okay? And with this equality, we consider this exact sequence. And remember, our objective is to conclude this equality, okay? Well, but this exact sequence says to us that the relative Bruce-Roberts number is equal to this dimension as a C-vector space minus this dimension, okay, as a C-vector space. By the Legros formula, we know that this dimension is equal to this sum, okay? So to conclude this equality, we need to prove that this dimension is equal to Turina number of X, okay? We know when X is an isolated hypersurface singularity, we know about this equality. And now we extend this equality considering X any ICEs, and we conclude this theorem. Okay, so when X is an ICEs determined by these functions, germs, and F is a function germ such that this number is finite, we have this relation for the relative Bruce-Roberts number. Okay? Well, now I will talk about the logarithmic characteristic variety, the LCX, okay? So now we consider, okay, X is our variety, and these vectors fields are the generators of the theta X, okay? So we consider U a neighborhood of 0 in Cn, and we have this set, LCUX. And the set is equal to the elements in the restriction of the cotangent bundle of Cn to U that satisfies this condition, okay, with I from 1 to k. And the LCX is the germ of LCUX along the cotangent space to Cn at 0, okay? Well, a remark about the LCX. The analytical structure of the LCX is given by these equations, okay? So it may not be reduced, okay? Well, now, Bruce and Roberts, they proved if a variety has codimension higher than 1, then its logarithmic characteristic variety is not Cohen-Macaulay. Okay? Nuno Balesteros, Oref Okamoto, and Tomazella prove that LCX is Cohen-Macaulay when X is a weighted homogeneous hypersurface with isolated singularity. And we extend this result, proving that LCX is Cohen-Macaulay for any isolated hypersurface singularity. And to prove this result, we use this relation between the Bruce-Roberts number of F with respect to X and the Milnor number of F. Okay? Well, we haven't answered the no-isolated hypersurface singularity case yet. And now, observation, okay, about the LCX. If a variety X is holonomic with logarithmic strata x0 given by this set, x1 to xs, then the irreducible components of LCX are y0 to ys with yi equal to the closure of the conormal bundle of xi, okay? And this equality as a set germs. So, as a set germ, LCX is equal to these unions, okay? And the LCX minus denote the closure of the subset of LCX obtained by deleting the component y0 coming from the logarithmic stratum x0, okay? And as a set germ, LCX minus is equal to this union, okay? Well, we call this guy, LCX minus, of the relative logarithmic characteristic variety, okay? Well, so a result, Bruce and Roberts, they prove the Bruce-Roberts number. If the Bruce-Roberts number is equal to the sum with I from 0 to S, if and only if LCX is Cohen-Macaulay in this point, okay? And the relative Bruce-Roberts number is equal to this sum, okay? And this sum with I from 1 to S, if and only if LCX minus is Cohen-Macaulay in this point. And in these sums, Ni is the number of critical points of a mercification of F on xy, and Mi is the multiplicity of the corresponding irreducible component yi of LCX, okay? This result is so interesting and important, okay? And interesting fact about the LCX minus, it may be Cohen-Macaulay even when LCX is not Cohen-Macaulay, okay? And it is the case when X is a weighted homogeneous ICES with codimension higher than 1, okay? Bruce and Roberts, they prove this result. And we extend this result, proving that LCX minus is Cohen-Macaulay for any ICES, okay? And to prove this theorem, we use this equality and this equivalence, okay? So now I will talk about the Bruce-Roberts number of F with respect to an ICES and the Milnor number. So now my objective is to prove a relation between these numbers, okay? So, okay. we know about the relation between these numbers when X is an isolated hypersurface singularity, okay? And when the hypersurface is weighted homogeneous, Nuno Ballesteros, Oref Okamoto prove this equality, okay? And we extend this equality, proving this other equality considering X any isolated hypersurface singularity, not necessarily weighted homogeneous, okay? Coriolis also proved the second equality, and he uses a different approach of us, and the works are produced simultaneously. Okay, but we want to know about the relation when X is any ICES, okay? And we have this example. We consider X, the ICES determined by this map germ, phi, and this function. So we calculated these numbers, and in this example, the Bruce-Roberts number is different of this sum, okay? So this equality is not true when X is any ICES, okay? But we want to know about the relation. And again, when we consider any ICES, we don't know the generators of theta X. And again, we consider the set theta xt, okay? And we use this characterization, and the first relation for the Bruce-Roberts number is the following, okay? Okay, this equality is not so good, okay, because we have this dimension and this other dimension, okay? So now we want to improve it, okay? Well, when X is an isolated hypersurface singularity, we know that this dimension is equal to Turina number of X, okay? And now here we also have this equality. So we want to prove that this dimension as a C vector space is equal to Turina number of ICES, okay? Well, a remark, if we consider P a generic linear projection, we have these equalities, okay? dp theta x is equal to this sum, and dp theta xt is equal to this sum, because this ideal is a subset of this ideal, okay? And the same happen here. Well, so with these equalities, we have that this dimension as a C vector space is equal to this other dimension, and we know that this dimension is equal to Turina number of X, okay? So to conclude that this dimension is equal to Turina number, we need to prove that this quotient does not depend of the function germ or X finitely determinate that we are considering, okay? Okay, and we prove this theorem. So we consider this map, okay, the evaluation map given by this way, and we prove that this map induces this isomorphism, okay? And this isomorphism says to us that this quotient does not depend of the function germ or X finitely determinate that we are considering, okay? And to prove this theorem, we use this lemma. And this lemma is so interesting because it exists an element in theta x satisfying this condition, okay? Then the vector field belong theta xt, okay? Well, so with this lemma, we prove this theorem, and we have the second equality, okay? And now we want to improve this dimension, okay? Okay, we have this result. Actually, this result is a consequence of the proof of this lemma. And the first point we have, if there exists a vector field in theta x satisfying this condition, then this element belongs to this module, okay? And with the first point, we prove these isomorphisms, okay? Now, look at this equality. this quotient appears here, okay? So this dimension as a C vector space is equal to the dimension as a C vector space of this other quotient. And in this way, we have the second equality for the Bruce-Roberts number. And remember, we want to relate the Bruce-Roberts number with the Milnor number, okay? And now we prove this equality, okay? And to conclude this equality, we consider this exact sequence, okay? And it says to us that this dimension as a C vector space is equal to this dimension plus this other dimension. But this quotient is isomorphic this other quotient, okay? And so we have that this dimension is equal to this sum. And now appears the Milnor number of F here. Okay? Okay. Now, a remark about this quotient. Okay? We know that this quotient is isomorphic this guy. Okay? And in this way, we have this other equality. I don't know how this equality is better, but the fact is, but using the second equality, because this conjecture, okay? So let R be a regular local ring of a dimension n, and I an ideal in R generated by a regular sequence with k less or equal n, and J an ideal in R generated by a regular sequence, this regular sequence, okay? Then we have this relation, okay? This length is equal to this combinatorial number times this length, okay? Okay, so it is a conjecture, and Born proves if I is a subset of J, this guy is isomorphic this module, okay? So with this condition, we have this relation, okay? We prove the conjecture in the case k equal to 2, and as a consequence of this particular case, we have this relation for the Bruce-Roberts number of F with respect to analysis of codimension 2, okay? So I finish here. Some references, more references, and thank you very much.
Are there any questions, comments?
Hi.
What? Oh.
So in your talk, there are many formulas where the terms Milnor number of x plus the Milnor number of the intersection of f inverse of 0 with x appear. Now, the sum of those two terms is the multiplicity of the module you get when you take the matrix of generators of the Jacobian module of x, and then you add on a row on top, which is a differential of f. Now, because you're working in the Cohen-Macaulay situation, the multiplicity of this module is just the co-length of the module. Now, my question is that if you can reduce everything back, or if you can reduce those mu terms back to the co-length of a module, can you get another proof by working directly with the Jacobian module, the augmented Jacobian module, and maybe these vector fields that are tangent to the singularity?
Could you repeat, please? Sorry.
Yeah, so one of the formulas that you had reduces to the, let's see, the relative Bruce-Roberts number is equal to, let's go back to that formula.
Here?
The relative Bruce Roberts number. That was in the beginning, I think. Huh?
This?
No, it's still not the relative Bruce Roberts number.
Ah, relative, okay. I didn't understand. Okay. Here.
Yeah, there we are. It's the bottom formula there. Okay, so this is the relative Bruce Roberts number is equal to the co-length of the module that you get by augmenting the partials of x with the partials of f minus the Turina number of x, which is the co-length of the Jacobian module of, let's see, is this going to be correct? Yeah, the co-length of the Jacobian module of x inside OXP. So you're getting the relative Brooks-Roberts number is the difference of two co-lengths.
Yeah, but the problem is that the model is not Cohen-Macaulay, so you cannot use this multiplicity as a collective.
No, it is Cohen-Macaulay. X is an ISIS. No, the problem is that the Turina number, when you mod out by the ideal of X, you reduced yourself to working, instead of working in the ONP, in OXP, right? Okay. Okay, but I'm sorry, it's all right. So so what I said actually is not quite right. It is the multiplicity of, no, that's actually is correct, yeah. The Turina number really is a co-length in this case. Okay. Anyway, that's.
Hi, it's more of a comment instead of a question. The thing is that if you take this, suppose, for example, if you go to the formula for the Bruce Roberts number, it shows that it is the Milnor number of F plus the relative Bruce Roberts number plus something. And the question is the following. If there is some geometric interpretation behind that, for example, in the hypersurface case, you see that if X is quasi-homogeneous, then the sum of the Milnor number plus the sum of the relative Milnor number, it gives you in some relative cohomology, because you have F, which is a hypersurface, and X, which is an ISIS or hypersurface singularity, and these two guys, you take Milnor fibers of both, and there is an exact sequence. In the middle term is a relative cohomology. So I think it is called like vanishing left-set thimbles. I mean, the theory of singularities. And the question is the following. If this analogous formula, geometric or topological, holds for ISIS, in the case of ISIS. And this would be very nice to know, because it would expand the theorem of Milnor-Palamodov type. It gives you an algebraic way to compute topological information, yeah? And this is the first comment, which is important, at least in my point of view. And the second one is a little bit more technical. It has to do with the Turina number of an ISIS, that it is the quotient of the modulo of vector fields, modulo the trivial ones. And I think, I'm not 100% sure, but I think that this has been proved also. I mean, it is implicit in the works of Alexandrov because he computes local cohomology and everything, and this formula exists there. Of course, the proof with taking a linear section is also important, but I think it should be referred somehow that it is there, in a sense. So that's my point of view for these things. And also that the relative, I think this is a very nice result, that this relative characteristic variety is Cohen-Macaulay for ISIS. It is important enough. And yeah, that's it.
No? Let's thank the speaker again.
Okay, good morning. Sorry for late. It's a pleasure to introduce Professor Osamu Saek's talk. He's from Kyushu University, Japan. Professor Osamu Saek works in the Institute of Mathematics for Industry at the Kyushu University. He has several important positions in the university, as for instance, director of the Institute of Mathematics for Industry, coordinator of Kyushu University leading PhD program in mathematics for key technologies, distinguished professor of Kyushu University, among others. Professor Saeki received in his career the following prizes awarded: Takebi Takahiro Prize in 1996 and Geometry Prize in 2015, both by the Mathematical Society of Japan. His main research interest is the global singularity theory of differentiable mappings. He's also interested in other fields as topology, differential topology, topology of low-dimensional manifolds, knot theory, and data visualization. The title is Topology of Ribbed Space of Smooth Functions on Manifolds. Please go ahead.
Okay, thank you very much. I'm very honored to be here to give a talk in this 70th edition of the Singularity Workshop. And I'm very happy, and also I would like to thank all the organizers, staffs. Thank you very much. For example, yesterday's event was, for me, it was a very good memory, and I think I didn't expect such kind of things. So thank you very much for everything. And so today I would like to talk about topology of Web spaces. But before that, just let me give you a good memory from my side. So my first visit to Brazil was in 1992, so exactly 30 years ago. And it was the second international workshop in San Carlos. The main purpose was that. And this is a photo of that occasion. And so it was 30 years ago. And I met, as you see in this photo, I met many people. Maybe some of them are here, like Jean-Paul is here, Sujin, of course, and Juan Ho also. And it was a very beginning of my collaboration with Brazil. And since then, in fact, it was my dream to be celebrated like this in the 60th birthday party in Brazil. And now it has been realized. Yeah, yeah, I'm very happy to see this. Thank you very much for everything. Okay. Okay, let me go into the mathematical lecture. So I would like to talk about Web space today. So the Web space can be defined for any continuous map between topological spaces. So let F be a topological continuous map between topological spaces. And many of you know that we define a very simple equivalence relation for X. The 2 points, X and X prime, are equivalent if they lie on the semi-connected component of an inverse image of the same image. So f of X is equal to f of X prime, and the X and X prime, they lie on the same connected component. And then this is an equivalence relation. And if you take the quotient, it will be denoted by WF. And this is a quotient space. And you have a quotient map QF. And then there exists a commutative diagram like this. So the original F is decomposed into the composition of two continuous maps. QF is the quotient map. And you see that F bar is easy to see that there exists such kind of a continuous map. And then the space WF is sometimes called a quotient space, but in this talk, I will call it the Reeve space of F. And in fact, for the function case, if F is a function, then WF is usually a graph. And so it is called a Reeb graph. But in this talk, I would like to call it Reeb space. Okay. And this is a very simple example. If you have a Morse function on the torus, like this, you have 4 critical points, and then its Reeb space. It's easy to see that this is a graph like this. Okay. So in the function case, it's very usual that the Reeb space has a graph structure. Okay. And it is known that if you have a Morse function on a compact manifold, then the Reeb space has a graph structure. And it has been mentioned, it is mentioned in Reeb's paper in 1946, but no proof. And as far as I know, there is a proof, rigorous proof in Sebastian Izar's master thesis. So, of course, he's Brazilian. He used to work in Rio Preto, and it was his master thesis, and there is a very rigorous proof there. But anyway, it is very well known that the Reeb graph, Reeb space of a function is very often a graph. But there are some papers that mention that Reeb space is really a graph, but in fact, I could not find a very good proof. They mention such kind of a fact. Yes, it is true, but no good proof. So I started to think about how we can weaken the condition so that we have a Reeb graph structure for the Reeb space. So this was my question. So given a smooth function, a smooth closed manifold, is the Reeb space always a graph or not? Closed means here compact and without boundary. Okay. And also, I was asked by Dominique if you work with path connected components instead of connected components, then we have the same result or not. And in this talk, I would like to consider these 2 problems. Okay. So now, first, the Reeb graph theorem. In the following, let M be a smooth closed manifold of dimension greater than or equal to 2. And for simplicity, we assume that it has no boundary and compact, closed. Okay. And F is just a smooth function. It may not be a Morse function. It may have a very complicated critical points. Okay. And the main theorem of this talk is this. So suppose you have, suppose the function you have, f, has at most finitely many critical values. Okay. And then the Reeb space has the structure of a finite graph. So this is my main theorem today. So f may have a lot of critical points, but here we assume that the critical values, you have only finitely many. Okay. And just a small remark, and the same result holds even if f has boundary, even if the source manifold has a boundary. As long as f itself and f restrict to the boundary, they have at most finitely many critical values. Okay. So finitely many critical values is a very good condition, and this includes already known results. But in fact, finitely many critical values, it's not a necessary condition. I will show an example. So suppose you have an arbitrary closed subset of the 0-1 interval. And then by Whitney, there exists a smooth function G whose 0 set coincides with C. C is any closed set. C, for example, can be a Cantor set, or can be very complicated. But anyway, you can find a smooth function whose 0 set coincides with C. And then you just integrate it. And then you get a smooth function on the 0-1 interval. whose critical point set coincides with C. Okay, and graph is something like this. So it has many critical points, and of course, H has this function has infinitely many critical values in general for a closed subset C. So this and in this case, it's very easy to see that the Rib space is just an 0-1 interval. Okay, and you can show that. So this function H has infinitely many critical values, but its Reb space has the structure of a graph. So this is a very simple example, and you can also construct for any n-dimensional manifold such kind of a function. So this means that the finitely many critical values is not a necessary condition in order to have a graph structure on the Reb space. But anyway, this is a very good condition, I think. So I just gave this example because in some papers they say that the finitely many critical value condition is a necessary condition, but it's not. Just to warn you. Okay. And another aspect is if you have a triangulable map, if the map between manifolds is triangulable, this means that you have a simplicial map between simplicial complexes, which is equivalent, topologically equivalent to this. And then the Reb space has the structure of a finite simplicial complex. So in the function case, if the target dimension is equal to 1, then the Reb space has the structure of a graph. So this has been known. This was a joint work with me and my student, George. And so if you have a function which is triangulable, for example, if you have a Morse function, it is known that it is triangulable. So WF is a graph. So this is okay. But there are some complicated function which is not triangulable. So for example, like this. So suppose you have a closed manifold and you consider any Morse function, and you take a regular value, and in the inverse image you have just a, usually it is just a codimension one submanifold. But here you insert any kind of a very complicated stuff here, such that this one cannot be triangulated. For example, the interior of this has infinitely many connected components. Okay, so such kind of a function can be constructed with the help of a bump function around here. So all these points are mapped by the new map F to value R. And so, of course, this is a critical value. So the critical value set increases by 1. And but nevertheless, this is a smooth function with finitely many critical values. So because of, by virtue of the main theorem of today's talk, the Reb space is a graph, even for this. But this is non-triangulable, so you cannot apply our previous results. But anyway, there are several complicated examples. And here I have another complicated example to show you that the problem is not so easy. First, we consider a smooth function phi 1 on the plane, such that the level curves are like this. So outside of this unit disk, the value is equal to 0. And inside the disk, you have 2 local maximum points and 1 saddle point. So it's like 2 mountains, okay? And but here, for the small disks here, the values are constant. So phi 1 is equal to 1 here. And with the help of this such kind of a smooth function, you just sum up the translates of this kind of a function. So translates means that here you have a disk, and on top of this small disk, you put this one again. So you have two mountains, and on top of each of the two tops, you put two mountains, and then on top of the 4 mountains, you put 2, and you continue this. And then what you get is a Cantor set. So here you have just 1 point. This means that the 0 level set is outside of the disk, so it is connected. So when you consider the Reb space, it is just 1 point. And so this one corresponds to the saddle point. And at the saddle point, you have 2 mountains. And for each mountain, you have 2 small mountains like this. So and then you take the limit. And then if you consider an appropriate weighted sum of these functions, you get a smooth function on the plane, such that the Reb space is something like this. So it's very complicated, and it seems to be a graph, infinite graph, but in fact it is not a graph. Why? Because here you have uncountably many vertices, but these vertices, they are not discrete. You know, each point is an accumulation point of the others. So this means that this has not a graph topology. So if you have a graph, the set of vertices, they must have the discrete topology. But here in this example, it is not. So this is a very simple, but on the other hand, it is a very complicated example. And so the Reb space seems to be a graph, but it's not. And of course, in this example, there are infinitely many critical points and also infinitely many critical values. Okay, so there are such kind of very complicated example. So you have to be careful in order to study Reb space of a general smooth function. And of course, using such kind of a function on R2, you can construct a similar function on any closed connected surface. Okay. So let me briefly explain how to prove our main theorem. So suppose you have a smooth function on a closed manifold of dimension greater than or equal to 2 with finitely many critical values. Then the first key lemma is the lemma 2.4. So for every critical value C, the critical value, critical level has at most finitely many connected components. And of course, if you have a Morse function, this is of course easy. But in general, for a general smooth map, it's not so easy to show this. And in order to prove this, we have another lemma. So suppose you have critical value C, and we take a very small positive number epsilon, so that C minus 2 epsilon, C plus 2 epsilon, this open interval contains no other critical values. Okay, because you have only finitely many critical values, you can find such kind of a very small positive epsilon. And then let X be the component of the inverse image of the half open interval C, C plus epsilon. So this half open interval does not contain any critical value. So of course, this one is a codimension zero submanifold. And if you consider the closure minus X, so the boundary of X, then it is always connected. So if X is a connected component, then this one, X bar minus X, is always connected. And so this is a key point, key part of the proof. And I will not go into the details of this proof of this lemma, but it is a kind of an exercise in general topology. Maybe not an exercise, but you just use how sort of compact or connected, etc., and you can show this. And once you have this, we can construct a graph, capital GF. This graph has vertices corresponding to the connected components of the critical level sets. As we have shown that each critical level set has finitely many connected components, so the vertices you have only finitely many because the critical values are also finite. And the edges correspond to connected components of F inverse R mu, where R mu are the maximal open intervals consisting of regular values. So the real line is divided into several open intervals by the critical values. So these are open intervals, and then the inverse image is a codimensional Zoro submanifold, and you take the connected components. And of course, there are finitely many, because we have assumed that the manifold M is compact. So this has only finitely many finitely many connected components. Okay, and then an edge is incident to a vertex if the closure of the component intersects the component of a critical level set. So this is well defined because of the lemma that I showed in the previous slide. So if you have a edge, you have, of course, two vertices incident to it, and this is guaranteed by this lemma. Okay, so this is connected. If it is not connected, you have to connect one edge to more than two vertices, and this will not be a graph. But here you obtain a graph. And I'd like to show that this graph, capital G, is homeomorphic to the Reeb space. And for this, you consider a function. And here, on the right upper side, you have the Reeb space, the quotient space, F bar, like this. So that this is usual one. And on the left bottom side, you have the graph. And because of this kind of construction, you can construct a continuous map, gamma F. And also, you have a continuous map phi from the Reeb space to the graph, which make the diagram commutative. So this is a consequence of the construction of the graph. And then, by the construction, we can see that phi is a bijection. And this is continuous. And WF is compact because this is a quotient of a compact set. And GF is a graph, so it is Hausdorff. And a continuous bijection from a compact space to Hausdorff space is a homeomorphism. And so this is the proof. So in a sense, I just use some general topology techniques. But the statement is that this quotient space as a topological space is homeomorphic to a certain graph. So this is the proof. Okay. And now I'd like to talk about another topic. It's about a path Reeb space. So instead of the connected components, if we use path connected components, what happens? So we do the same definition, but here we consider 2 points to be equivalent with respect to P if they lie on the same path connected component of a level set. Okay? And you have exactly the same, similar commutative diagram. And here you have this space. And here in this talk, we call this space path Rave space of F. Okay. So as this is a equivalence relation, you have the quotient map, and here you have the quotient topological space. And in fact, this is a very pathological space, we will see. So for that, let me give you a very simple lemma. Suppose you have a continuous map, and you assume that the target space Y is a T1 space as a topological space. So the one point is a closed set. And then so it's the Rave space. So this is a usual Rave space, not a path Rave space. So the usual Rave space has a very good property. So for example, if you have Y as a manifold, then of course its Rave space is a T1 space. And the proof is easy, so I will skip. Just an easy exercise of general topology. So in order to show that Rave space and path Rave space, they are different from each other, it's not so difficult. So suppose you have a closed manifold, and then it is very easy to construct a compact set K, which is connected, but not path connected. So if you consider equivalence relation with this, then the result is different in general. So for example, if you consider a smooth function such that whose zero set coincides with K, this K, then the WF and WFP, they are not the same, because the equivalence relations, they are different. Okay. And also, if you have a manifold, then you can always construct a compact connected set K containing a path component that is not compact. So if you have a compact, and you can consider a compact set, but it may contain a connected component, a path connected component, which is not compact. And this can be constructed. And in this case, the path Rave space of the resulting smooth function is not a T1 space, because this corresponding path component is not closed. So in this case, WF is T1, but WFP is not. So they are, of course, topologically distinct. So the path Rave space and the Rave space, they are not homomorphic to each other in general. And here is an explicit example. You have S2, and on the left-hand side and the right-hand side, you have delta 1, delta 2. They are just disks. And in the middle, you have an annulus, and on the annulus, you have an orbit like this, which accumulates to the boundary of delta 2, and on the other hand, it accumulates around the boundary of delta 1. So you can construct such kind of a set C, and then we consider the union of these. And we can show that this is a compact, connected set. But as you see, it has 3 path components, okay? And in this case, we can construct a smooth function on the 2 sphere whose zero set coincides with compact set K. And outside of the compact set K, you have to be careful to construct a smooth function. It must be a smooth function. And in order to get a smooth function, for example, here you have to be very careful so that you can you can do differentiations. But anyway, you can do that. And the result is a very complicated smooth function on S2. But as you see, it has only 2 critical values, minimum and maximum. So minimum is 0 here, and maximum is somewhere outside of C. And it is a smooth function whose Reb space is just an interval. However, if you consider the path Reb space, path connected component is different from the usual connected component. So here you have 3 path components for just one connected component like this. So this means that you have 3 points here. But as this space is not T1, you cannot embed it into R2. So it's very difficult to draw the picture. But anyway, it's something like this. You have 3 points here, and you have 3 corresponding to the connected path components of the set K. And so VC is not closed here. In fact, its closure coincides with 3 points because, the closure of C intersects with delta 1, delta 2. Okay? So this is a very complicated example, but anyway, so like this, the usual Reb space has a very good behavior compared with the path Reb space. So to use the connected component is very good, but maybe it's not so good to use path components. Of course, if you work with triangle maps or functions, it's okay. But in order to work with general functions, to use path component is not a good idea. Okay? So that's what I wanted to say. But before closing my talk, I would like to announce some. So the subject is completely different. As I am the unique Japanese participating in this conference, I would like to advertise some of the Japanese meetings in Japan. So from October, December this year, this will be they are special singularity theory months in Japan. And we have 5 meetings planned. So the first one starts in October, and the last one in December. And many of the conferences, they are already organized, and speakers have been, many of the speakers have been already fixed. But for example, the first one is still according for application of a talk, but deadline is in 3 days maybe. So if you want to participate in such kind of a conference, please visit these URLs. And this morning, I think the organizers of this conference sent you an email about this. So please consider participating in this. Of course, they are all of them will be in hybrid format, so you can participate online. And of course, if you want to come to Japan, you are very welcome. Okay, thank you very much for your attention. Thank you very much for listening.
Okay, questions, comments? Please use the microphone if you want.
Do you have any simple conditions for when the path Reeb space is the same as the Reeb space?
Path and the usual one? I don't know. So usually path component and the connected components, they are different, of course.
Yes, that would do it, certainly.
But I don't know if there are some conditions. For example, if you have a locally path connected space, but it will be okay. But even if you work with manifolds, the inverse image of a point can be very complicated, and it may contain connected components which contains more than 2 path connected components. And so I don't know. Of course, if it is a triangle function or map, it's okay. But in general, I don't know.
It seems like the requirement that the path component read space be the same as the component read space gets rid of a lot of possible pathologies that a function could have. So it made me wonder if you could try to use it to describe or to sort homeomorphisms from good homeomorphisms and bad homeomorphisms. So, you know, you have a homeomorphism in a function whose path component read space is the same as the component read space, and then you ask that the compositions also have the same thing, and then the homeomorphisms can't be too bad, perhaps.
Okay, thank you very much for the suggestion. Yeah, it can be a very interesting problem. Yeah, thank you.
More questions, comments? Okay, let's thank again.
Thank you very much.
We have another gift for you. Just wait a minute, please.
Wow.
So these are some gifts that in the name of the organizing committee, the group of singularities, and several several people that really love you. Okay.
Wow. Oh my God. Thank you so much.
Okay, I got a message again for the lady from the payment desk, and she told me that actually, even for those that have gotten the partial payment, should come back there to get the remainder, okay? So I'll repeat again the names: Aline Bartel, Benjamin Bod, César Augusto Zapata, Christian Cabelo, Dominique Brasido, Graham Mark Reeve, Inácio Ribes, Jean Tim Wessing, Jawad, Jean-Paul Bracelet, Juan Rua Balesteiros, Marcos Pivakov, Matias Zack, Michael Farnick, Nicolas Duterte, Patrício Quadros, Raul Zé, Remy Langevan, Roberto Conejeiro, Saurabh Trivedi, Staniel Ianesco, Terence Gaffney, and Thomas Pelk. Okay, please, after lunch, maybe we can go a little bit before, 30 minutes before. The payment office will be open more or less until more or less 1:30. Okay, so 3 minutes before the first plenary talk on the afternoon, after lunch. Sorry. Okay. Okay. A partir de 1 hora. Sorry. Okay. The payment office will be open. Sorry. Regine just told me the payment office is open from 1 p.m. to 5 p.m. Okay, anytime, please go there. Thanks.
Okay.